Hello everyone and welcome to another Stat 437 lecture video. In today's video we are going to be talking about fitting proportional hazards models in R. So over the past couple of lectures we've been looking at what are proportional hazards models and what are the mathematical details of those models. And in today's lecture we're actually going to see us fit some of these models for the first time in R. So we're going to talk about a new R package which can allow us to fit these proportional hazards models, as well as discussing through some sort of how we interpret with these models, uh, how we can do some hypothesis testing, all of the usual stuff that we've gotten used to seeing when we're working through these models. So all of the code that we're going to be looking at today is posted on the course website. The data set that we're analyzing is also posted there. If you have any questions, of course, let me know. And with that, I will open up R and we can get started talking about proportional hazards models. So the first thing that I want to note is that we're going to be working with this library EHA. So it's a package in R, uh, events history analysis, and I can load it in. This package actually relies on the survival package that we've been working with. And the reason that that's kind of nice for us is because the proportional hazards model is going to take a very similar form when we're fitting it to the servreg function that we had seen before. So we're still going to work with those serve objects. It's going to be quite familiar for you if you've been following along. Now, the primary function that we're going to be working with is this phreg function. So if I just pull open the documentation here, you can see that it's roughly speaking going to be similar to what we're used to seeing with these types of regression-based models. So we specify a formula, we give it a data frame, as well as sort of specifying the distribution that we want to work with. And you can see that there's the Weibull distribution, there's the extreme value, PCH to allow us for piecewise constant. We'll talk about that a little later. Log logistic, log normal. And then it indicates here that the exponential can be obtained as a special case of the Weibull with shape equals 1. Okay, and so we've seen that in terms of our theory, where we saw that the exponential distribution is a special case of the Weibull distribution, but when we're specifying it in terms of the phreg function, we'll have to specify that sort of explicitly. Now, the data that we're going to be working with here is mortality data. It's available on the class website, and so I'll just read in the CSV file here, and then we can take a look at what the form of it is and sort of see what we're working with. So if I read this and just take a look, you can see that it's, for the most part, it's a fairly standard data set that we're used to looking at. So we have an ID column. We have this event indicator. So a 1 is the event actually occurred. And in this case, event is actually death. So we're analyzing mortality data here. You can see that we have this birth date, which is sort of stored in this strange decimal format. And then we have this socioeconomic status indicator. So it's either upper or lower, depending on the individual's economic status. Now, this thing that's slightly different about this data set compared to what we're used to looking at, there's actually sort of two differences. The first is that we have 2 times instead of just 1. So we have the time that the individual entered into the study, and we have the time that they exited the study. Now, if they exited the study because they were censored, they get an event indicator as a 0. If they exited the study because they died, then the event indicator is a 1. So we can see that the second individual entered the study at 3.47 years, and then they exited at 17.562 years, and so they were in the study for just over 14 years. So they had 14 years worth of survival. Now, the idea with these data are that they were looking at men who were over the age of 40, and so this is just an indicator of sort of when they came into the study. So instead of working with a baseline and we're just measuring time since baseline, in this study we get both their start time and their stop time, and that might not be at the 0, right? So this is, we'll sort of look through how we can fit serve objects when we have data in this format. The second thing to note is that we actually have multiple records for some of these individuals. So you can see for individual 3 here, we have 2 different lines. And if you look at it, what you'll notice is that first, the exit of the first line is the entry of the second line. And the thing that changes is the socioeconomic status indicator, right? And so what's happening is at the time at this 13.463, the person actually went from being a high socioeconomic status to a low socioeconomic status. Okay, and so then it's divided into these two lines where what we're sort of thinking about is as though we had one individual who had a high socioeconomic status who was censored at time 13.463. And then a second individual entered the study in at 13.463 and at this point they were censored at the end where they were lower the whole time. So in this way, we're sort of thinking about these different iterations over the time varying socioeconomic status as different individuals. Now, this isn't the only way that we could analyze these data. You could collapse these back together and then look at someone's baseline socioeconomic status. You could, include an indicator as to whether the socioeconomic status changes. There's a bunch of different ways of looking at it. But for our purposes to sort of demonstrate with these data, all I'm going to be doing is sort of treating each individual observation as though it were a different person, and that's going to work well enough for what we're trying to do here. But just note that that is kind of a strange formatting consideration with these data, and it's worth sort of thinking about if you want to play with this in a little bit more detail. But so with that, we can actually begin to fit some proportional hazards models. So the general idea is that we're going to be calling PH reg, and the formula is going to look a lot like it did for the servreg function. So we want to pass in a serv object. Now, as I was just mentioning, we have those 2 times in the study. And so the serv object actually can include up to 2 times, where the first time is the entry point, the second time is the exit point, and then there's the event indicator. So this is all very well formatted for this. So we would go enter, exit, and event, and we'd want to explain this with respect to the socioeconomic status. Now, I do want to just make sure that our socioeconomic status is considered a factor, and so I'm just going to come up here and make sure that that's included beforehand, just so that we don't run into any issues with that. Then I can pass in the data here, and we can pass in the distribution. Now, let's say that we want to start with an exponential model, right? So we saw that in order to fit an exponential model, we should specify the distribution to be Weibull, and then we explicitly say that the shape parameter needs to be 1. So I'll call this model just simply model 1 and sort of reformat this here, make everything a little bit clearer, but we can run this and we get this model fit. Okay, so I can take a look at the model object here, type model 1 into the console, and we can see that it looks quite similar to what we're used to looking at with these regression models. So we get our call up at the top. Then we have these sets of covariates, which we'll come back to in a moment. That's sort of our coefficients table there. You can indicate that the shape parameter is fixed at 1, which tells us we were doing the Weibull forced to be exponential. And then we're given some summary information down here, the number of events, the total time at risk, and remember that we can use these 2 different values here to actually estimate the hazard in an exponential model. There's the likelihood and then the likelihood ratio statistic, etc. The point that we really care about is up here on this covariate table, right? And so essentially for every factor in the model or for every variable that you include in the model, you're going to get a listing here, right? And so the reason that this looks a little bit strange is because the function sort of takes factor variables to be a little bit different. So we can see here that we're dealing with the socioeconomic status factor, and then it gives us a listing for both levels. So we used to be only thinking about having 1 listing, right? It would only be sort of this upper row, and the lower row is considered the reference category. And here it lists the lower row as being the reference category. And you can see over in this coef column here, the coefficient is estimated to be 0 for the lower. And so that's the same thing as not including it, but this function sort of just explicitly lists that there. So the pieces of information that we're really concerned with right here, this -4 or 0.484, is the coefficient in our proportional hazards regression model for individuals who are in the upper socioeconomic status. Then it gives it to us exponentiated, which can save some time in terms of doing the computation ourselves. We get a standard error, and we get this walled p-statistic here. Okay, so the test of significance tells us that this is significantly different from 0 because our p-value is significant. Okay, and so if we had more factors in our model, you would see sort of more rows in this table here. We also see that we get this log scale parameter, and just like in the servreg, this is going to be the scale parameter for the distribution. This is sort of the log of our row parameter, right? And so we get an estimate of it. It's under the coef column as well, and then we get a standard error as well as the Wald test of significance there. And so we can see it's significantly different. And so all of that is sort of standard fare for what we're used to looking at this point. But now, instead of them being linear regression coefficients, they are coefficients for our proportional hazards model. So, what can we do with it? Well, we can start to try to, say, extract the hazards from the model, right? And so if you think about it, we would have two sets of hazards in this model, right? So the way that the proportional hazard model works is you have your baseline hazard, and then you multiply that by that exponential of the linear predictor. And in this case, that exponential linear predictor is either going to be for someone who is in the lower socioeconomic status or in the upper socioeconomic status, right? And so because of that, we're going to have one hazard that is assumed to be constant for all of the individuals in the lower socioeconomic status, and one that's constant in the upper. And so we could take H lower, and we want to sort of get the hazard estimated out of this model. Now, there's a couple of different ways of us doing this, but the first way to note is that if we take a look at sort of model 1 here, and I'll do this before assigning it to a variable, if I take a look at model 1 coefficients, you can see that the first one is this socioeconomic status upper variable, and then the second one is this log scale. And so if I just grab the second one there and I exponentiate this, this is giving us our row parameter, right? So this would be rho in this distribution. And we know that for someone who is in the lower socioeconomic status, that the eta is equal to 0. And so their total hazard is going to be the baseline hazard times by e to the 0, or times by 1, right? And so hazard of lower is going to just be 1 over rho. Okay. Now, for someone who's in the upper socioeconomic status, we know that their hazard is going to be equal to the baseline hazard, so h0, times by e, in this case, to the power of whatever the coefficient is on the upper, right? And so, say right there, e to the upper. And so we can go h upper is going to be equal to 1 over rho times by the exponential of model 1 coefficients, and in this case it'll be number 1. And so then we could look at what the hazard is assumed to be for the lower, and we could look at what the hazard is assumed to be for the upper, and you can see that the hazard is higher in the lower as compared to it. It's about twice as much, not quite. But so what that's suggesting is that individuals who are in the lower socioeconomic status have a higher chance of mortality sort of at any given point, assuming that this exponential distribution fits particularly well, right? Now, we could also have included other factors in the model here, right? And the model is going to look much the same way, right? So if I had gone instead, and I had done something like model 2 could be PHRAG, where we take the serve of enter, exit, event. Instead of just socioeconomic status, I could also say include the birth year here. The data is still going to be the mortality. Let's say that we're still using a Weibull distribution with shape parameter equals 1, so we're still using an exponential. And, oh, I guess it's not called birth year, birth date, sorry. It's called birth date in the data here, and you can take a look. And now we're going to have a very similar output, except instead of it just being the socioeconomic status indicators, we also have this effect of our birth date, right? And you can see it does appear that maybe it's significantly different. All right, so the general output, oh, and then I guess in this case, in terms of estimating hazards, we're now not only going to have a hazard for the lower and upper socioeconomic status, but you'd also have to include someone's birth date in that, right? And so then each person is going to be working from the baseline hazard, which will be approximately the same type of thing here. Rho is going to be a little bit different, but more or less equal. And then, we can work from there. But in general, this second model isn't actually a particularly good model. I just wanted to show you how we could think about adding additional factors and show you that it's, roughly speaking, the same type of thing. Okay, so we could start talking about doing some different forms of inference here. For instance, what if we wanted to get a confidence interval around the hazard ratio? And so we'll work from model 1, just because model 1 is sort of a nicer model to work from. But if we wanted to know the hazard ratio and say between high to low, so socioeconomic status, right? So the hazard ratio itself is simply going to be the exponential of the coefficients from model 1, and it's just the first one right here, right? And so we can look at what the hazard ratio is, and it's this 0.616. Now, if we quickly take a look at the model output again, you can see that this is sort of given to us as the exponential of this coefficient here, right? And so we sort of could have read that from the table directly, but this is where the hazard ratio is given. And so what that's saying is that at any given point, the hazard for someone who is in the high socioeconomic status compared to someone who's in the lower socioeconomic status is going to be about 60%. They have about 62% say the hazard. Okay. Now, if we wanted to do a confidence interval on this, well, we're going to be using sort of our standard walled procedure here, right? And so we know that we would take our estimate, and inside of the exponential here, we'd want to subtract off the Q norm of, say, a 95% confidence interval, so 975, times by, and we want the standard error of our estimate. And so if we come in here, we can say the standard error is going to be the square root of the diagonal, and we can grab this from model 1 var here, and it's going to be the first term of that, right? Because if we look at this model 1 var here, you can see that it gives us the variance, covariance matrix. And so coming here, that will define our standard error, and we can get sort of our lower bound and doing the same type of thing here, except adding on to it, we can get our upper bound, right? And you can see, so the estimated hazard ratio is going to be somewhere between sort of a 0.49 and a 0.78 on a 95% interval. Okay, so that sort of is going to be all of the same types of things that we could do here. You already saw there's the p-value from the walled test, but of course we can also just grab the standard error and run the same types of tests on any of the coefficients in the model. All of that's going to be quite similar to what we've been doing throughout as well. So maybe as a third model here, what we could do is instead of constraining the shape parameter to equal 1, we could look at allowing this to be sort of arbitrary. And so I'll do another pH reg here, where we go enter, exit, event, and we're just using socioeconomic status still. This time we'll specify the distribution to be Weibull, and we'll specify the data to be Mort, but we're not going to actually specify a set shape parameter. So we look at the model 3 here, we can consider this output down here, and you can see that now instead of just getting the log scale estimate, we also get a log shape estimate. And you can see that our log shape estimate is 0.331, and so if we were to exponentiate that, you can see we get about 1.4, and so it seems like actually probably our estimate is quite a lot higher than 1, right? If we look at the hypothesis test, this is a test of it being equal to 0, and if it were 0, then that would correspond to a shape parameter equal to 1, right? If the log equals 0, then the shape parameter equals 1. And so you can see that that seems to be not the case, which would sort of suggest to us that a Weibull where we're not constraining the shape parameter is a better fit to this distribution. Now we can also sort of start thinking about trying to plot out these hazard functions, right? That's a common way of looking at our models here. And so the first thing that we would want to do is take a look at getting our kappa and our rho parameters from the Weibull distribution here, right? So I'll just note that we're trying to plot the hazards here, right? And so kappa is going to be given by the exponential of the coefficients for model 3. And if we just look at those coefficients for a second, you can see that we have our socioeconomic status as the first parameter, then we have our scale, and then we have our shape parameter. And so kappa is going to be the third one, and rho is going to be the exponential of the coefficient for model 3, this time the second one. So we can define our kappa and our rho, and we can see that kappa is 1.4, which is what we had seen before. Rho is about 36, right? And so then what we could do is actually start looking at the, say, the hazard for the Weibull distribution. Okay. Now, the form that this takes on, if you don't remember, that's quite all right. But so the form is going to be kappa times by rho to the power of negative kappa times by t to the power of kappa minus 1, right? And so if we just take a look at this final term here, in the exponential distribution where kappa equals 1, it disappears. But one of the nice parts about the Weibull distribution is that the hazard function is allowed to vary with respect to time. And so because of that, you can see that if kappa here is larger than 1, then we're sort of going to be increasing with respect to time. As time increases, so too will the hazard. And if kappa is less than 1, then we'll end up with sort of 1 over t, and it will be inversely proportional. So in our case, we see the kappa is about 1.4, and so we should expect our hazard to be increasing over time. Okay, and so what I'll do here is actually just very quickly define a function that gives us the Weibull hazard. And so it'll be a function that takes in kappa, rho, as well as some time here. And it's just going to actually equal this value that I've typed out here, except I'll have to come and replace these curly braces with some rounded brackets, but we can do that. And what this is just going to do is just return the value for the hazard function at any given time. And so I can come down here and I can give it our kappa, a rho, and some value, and you can see that it outputs a hazard for this. And the reason that I want to do this is just because I think it would be nice to plot over the hazard function for the Weibull, and we could plot alongside that what the hazard was estimated in the first case when we were just looking at the exponential, and sort of see why the Weibull provides us a more flexible model here. All right, so I'm going to define this times variable. It's going to be a sequence between 0 and 20, and I'll just let the length of the output be, say, 200, just to give us a nice smooth line. And then what I want to do is I want to plot the Weibull hazard, where we give it the kappa, the rho, and these times. And I want to plot those with the x-axis being times here. I'll say that the type is going to be line, and I can just run that. And you can see that we get this increasing hazard function, right? And actually, if I increase this maybe a little bit more, up to 2000, it'll take a little bit longer to plot, but it gives us a smoother plot there, okay? Now, in the case of the exponential distribution, we know that the exponential distribution has a hazard in general over the whole distribution of just simply 1 over this row, right? But we've overwritten rho, and so I'll just come and grab this here. And alongside this, what I want to do is say plot, or we'll add it with lines so that it plots on the same plot. And we could do the Weibull hazard here, where instead of it being kappa, we pass it a 1. Instead of rho, we pass it 1 over the value from the first model. And we should still pass it in the times parameter here. Plots with respect to times, we can set the line type to be, say, 2, so that it shows up as a dotted line on the plot instead. And, oh, my bad here. This should not be a negative 1. This should be just a positive 1, because this is our rho parameter, not our hazard directly. So if I do that, you can see we get this dotted line added to the plot here. And that's our hazard if we were to assume the exponential model was correct, right? And so obviously the Weibull model provides sort of a more flexible model in this situation, and something that seems sort of more realistic to what we'd actually expect. As someone ages more and more, their risk of mortality should be increasing, whereas the exponential is going to overestimate the risk early on and then underestimate the risk near the end. Right? But we also saw this idea of using a piecewise constant hazard, right? So instead of using the exponential directly, we said, what if we use an exponential except over sort of cuts on the line, right? And so we can do that in this EHA package as well. So I'll come in here and I can define, say, model 4. And in this case, instead of using the phreg function, we're going to use the pchreg function here. But otherwise, it will be exactly the same. So we'll pass in the serve object where we have our enter, our exit, and our event. Give it the socioeconomic status. Now, we will pass in the data here as well. We don't have to specify a distribution because the pchreg is only going to be doing a piecewise constant hazard. And here, instead of the distribution, what we want to do is specify a set of cut points for our distribution. And so the way that we would do this is we just pass in this cuts parameter, and then we can just pass it in a vector of where we want the cuts to be. So we could say every 4 years. So we do 0, 4, 8, 12, 16, and 20, right? And if we run this, and I come in here, you can see that my model 4, if I scroll this up, now we get our socioeconomic status indicator, but we don't actually see sort of any other parameters being estimated. And the reason for that is because there's not one shape or scale parameter. Instead, we're estimating different shapes and scales on each one of these intervals. And so then you could ask, how do you get to those? Well, those are stored in model 4 hazards. And so you can get here, and I can show you down here on 0 to 4, the estimated hazard is this 0.013. On 4 to 8, it's 0.015, and so on, right? And just to compare this to what we were looking at before, H lower, as you can see, it's a 0.02 for the lower case, and so that sort of sits in the middle of all of these hazards that we estimated here, right? So that makes some level of sense. And then the idea would be that the hazard for an individual who is in the upper socioeconomic status is going to be equal to the hazard in this interval times by e to the coef, which in this case is 0.618. So these would represent the hazards for the people in the lower socioeconomic status. And if you multiply it by this 0.62, then you'd get it for the people who are in the upper socioeconomic status. So what we could do here is actually try to add on these piecewise constant hazards onto the plot here. And so what I want to do is create sort of a set of points where we have our starting and ending y value, which is going to be constant over each of these intervals. And so the way I'm going to do this is call this rep function, which allows us to repeat a vector. And so if I call it rep on the hazards, and I say each equals 2, then if I just run this down in the console, you can see that what's happening is it's just duplicating each of the elements into the list here, right? So you see 2 of the first one, 2 of the second one, and so on. And so those are going to be my y values. And then for my x values, then what we want to do is essentially the same thing, except on this list, and not exactly correctly. But so if I do here, I want to replicate each of these individual values in the middle here. And so I'll show you why in just 1 second once we get these all written out. But if I do this, now you can see my x's start with a 0, and then we have a 4, and then we have a 4, 8, and then an 8, 12, and so on. And if I just add these lines with our y's by our x's with line type equals 3, and the color, let's say, is red, just to make it stand out. Should be a string there. Then you can see that we get this piecewise constant hazard plotted on here. And so what I'm doing with that call is actually for the each of these line segments has the starting and ending y value being the same, which is why we replicated those values. And then for the x's, it's going to be a 0 and then a 4. And then we repeat the same x value of 4 and then an 8, and then an 8, and then a 12, and then a 12, and then a 16, and then a 16, and then a 20, right? And the y values are going to be replicated so that we get the same endpoints. So hopefully that makes sense. But you can see that plotting over this, we allow to get sort of a similar shape to the Weibull distribution, but we're not constrained to the same smoothness. And then, of course, we can always add more cuts. If we think more cuts are appropriate, we could add fewer cuts. We could start testing whether the hazards are different within these different intervals and so on. Sort of the possibilities there are somewhat endless, okay? But so that's sort of going to be your process, and then otherwise it's going to be quite similar to everything else that we've been doing throughout the term, right? If you're asked a question, you can translate that question into a statement about the parameters, and then work from there, right? And so with that, the last thing that I really want to show you is this connection between the proportional hazards model and the accelerated failure time model, and that's through this Weibull regression. Right, so the model that we've been working with so far, which was model 3, is already a Weibull regression model, right? But I'm going to define one final model here, so we'll do model 5, and I want this to be an accelerated failure time model from the survival function. So just to briefly recap, this would have been serve reg, And just to show you here, we can do serve, and we would do enter, exit, event, socioeconomic status. The data is going to be the mortality data. The distribution is going to be Weibull. Now, this servreg here is going to sort of get angry at us when we're using this type of a survival object here, right? And so we've been working this whole time on data that is using the enter, exit, event formulation. Now, I had mentioned at the beginning of the lecture that EHA is sort of actually built on top of survival. And so one of the functions that the EHA package provides is an accelerated failure time regression model. So if I do, I believe it should be called AFT reg here. You can see that AFT reg is accelerated failure time regression, and it sort of provides all of the same types of options here. But the one difference here is that oh, I guess I will have to type out the full distribution for this call. But the difference is that it actually allows for this sort of object type. Otherwise, it's just calling the survival package under the surface. And so we could have been working with this EHA package for accelerated failure time models as well. But I wanted to point out that sometimes in this survival data context, you're going to need to be able to use something that sort of relaxes that assumption a little bit. But regardless, our model 5 output is going to look very familiar to us at this point, right? And so we get our lower and upper values here, and then we get our log and our scale and our shape parameters estimated here as well. But the thing that I really want to focus on is taking a look at the model 5 coefficients, and next to them, I want to look at the model 3 coefficients, right? And so I can run both of these here, and we can take a look and see, so here is our accelerated failure time coefficients, and here are our proportional hazards coefficients. And so the first thing to note is that actually with the way that they are reported for the model 5 here, you can see that we should get the same log scale parameter, right? So the log scale parameter is the same. Now, I will point out sort of how we talked about that before in a few moments, but what I want to do next is focus into this socioeconomic status indicator. And we had said in our lecture that if you have an accelerated failure time model with, say, beta star as the coefficients, and you have a proportional hazards model with beta as the coefficients, then we said that this relationship was going to be given by beta star equals -1 times beta divided by the kappa parameter. Now we can, clearly look at these and see that this relationship does not appear to be holding. And so why is that the case? Well, the issue is that with this AFT reg function, there are actually two different parameterizations of the model. And so if I look at the documentation for the AFT reg here, you can see that if I come down here, there's this param call, and it says that which parameterization should be used, and then importantly, if you provide it with life exp, it uses the same as in the servreg function. And the reason that I wanted to bring this to your attention here is just that in the literature, you're going to see different ways of writing down these same models. You're going to see different ways of writing out the distributions that we're talking about, but you're also going to see people write out an accelerated failure time or a proportional hazards model quite differently, depending on sort of the source that you're looking at. And so it's quite important to note that while this parameterization is actually, in fact, correct, the default in the EHA package is different than the default in the survival package, even though they're built on the same sort of core mechanic. And so if I come in here and I specify this parameterization is equal to the life exp, then you can come run that model again. It still fits. And now if we look at it, model 5 coefficients and model 3 coefficients, well, we can see that at least now it's plausible that this relationship could hold because the signs are different here, right? So we still see that the log scales are the same, and we'll get back to what that means exactly in just a moment. But what I want to focus on is showing you that this relationship actually does hold. And so what we would be saying is that this model 5 coefficient should equal this model 3 coefficient divided by the exponential of this. And so does it? Well, we can take a look here and say model 3 coefficients, model 3 coefficients, and we divide 1, take -1 times by that, divided by the exponential of model 3 coefficients, and in this case it's the third. And if we run that, we get 0.347818, and just to confirm with ourselves, model 5 coefficients 1 is 0.34785. And so, slightly off because of the different numerical optimization, but you can see that roughly speaking, those are the same, right? So this relationship is holding. Now, when we also talked about the accelerated failure time method, I had talked about using an intercept and had indicated that in the proportional hazards model, we don't use intercepts, and that's because it would get caught up in that baseline hazard. So when we use EHA to fit, instead of fitting to an intercept, they give us this log scale term here, right? And so when we were walking through the theory, what I had said is that the log of the rho term from your proportional hazards model is going to equal your beta 0 in your accelerated failure time model, which is exactly what we have here, just within the EHA package, they call it the same thing. Okay, so this is our beta 0 from our accelerated failure time model. This is the log rho term from our proportional hazards model. They are mathematically the same object here, but we can see that they're sort of labeled differently than we might expect. But the sort of core issue here is that what that means is that when we have our Weibull coefficients, if you'd rather interpret them as an accelerated failure time model, we can do that because we just do the conversion from our proportional hazards to the accelerated failure time. And same thing in reverse. If you have accelerated failure time coefficients, you can interpret them as proportional hazards by taking the negative of that times by the exponential of that. And so hopefully that all makes sense. Hopefully that all connects. And hopefully the confusion of the sort of landscape of survival analysis packages in R is you can overcome it using a little bit of the documentation reading, because certainly it can get confusing to see the same types of models being fit in the same manner, but giving you different outputs than you might expect. So hopefully that walks through a few of the different hiccups that you might come by when you're working through all of this. And ultimately, that's everything that I wanted to talk about in this lecture. So this is going to be the final lecture of the semester. We've covered sort of all of the content. You now have everything that you need to complete the assignments in this course. And for the remainder of the semester, you'll mostly be working on your final projects. Of course, if you have any questions about anything that was in this video or in any of the other lecture videos, please reach out and ask me, and I will happily do my best to answer. If you need any sort of additional supplementary material, we can look at whatever that's needed. You can book office hours, all of that stuff. So I'd like to thank you all for your attention throughout the term, and hopefully all of this was clear, and good luck with the rest of the content in the course. And if you need anything, you can reach out via email or on Teams. Otherwise, thank you all for watching.